Hello everyone. My name is Guedong Park, working in Professor Hyun-Suk Group in Seoul National University in South Korea. And today I'm going to talk about the extending classically similar to bounds of Clifford circuits with non-stabilizer states via framed beginner function. This research was worked by me, Guedong Park, and Professor Hyun-Suk in SNU, and Professor Hyuk Jung-won in KIAS Korea. So before we report the main results, I want to briefly introduce about the classical simulation of quantum circuits and the discrete beginner function as another simulation scheme for classical simulation of quantum circuits and its limitation to qubit system. As previously, the Professor Rosendorf explained those sections very well. So actually, you might feel very comfortable with those sections. And sorry for numbering. We're gonna explain the generalized concept of Wiegand function, frame Wiegand function, and frame changing rules, and several main results we've gotten. So what is the classical simulation? So we have a quantum circuit. So we have zero states inputs and intermediate quantum channels between them, and the final Pauli measurements. So the main task of quantum circuit is located in the binary measurement string under the probability distribution, Born probability distribution, which is written as simple mathematical form. So when we can simulate, when we can obtain the outcome exactly following this distribution without having this quantum circuit as in reality, then we say we classically simulate these circuits. So this is a classical simulation. But the main reason we need quantum circuits in real is actually there are many examples of quantum circuits which cannot be classically simulated via the classical computers, such as Shor's algorithm or Deutsch's algorithm. But still, we can say there are other several cases of quantum circuits, several classes of quantum circuits which can be classically simulated in polynomial time. So the typical example is the Clifford circuits, consisted by the computational basis as an input and Clifford operation and Pauli measurements, including intermediate Pauli measurements and post process. And this circuit can be classically simulated via classical computers. And there are other cases we can classically simulate. So if, for example, when the circuit has a large polarization noise between each gate, or a circuit had shallow depths neighboring quantum gates. Now we're going to introduce another simulation scheme for quantum circuits, and to do so, we're going to introduce the discrete Wiegand function. And actually, Wiegand function formalism is more famous in the continuous variable regime. But in analogy, we can establish the Wiegand formalism also in the discrete variable regime, discrete variable space. So instead of displacement, so as a displacement operator, we define this generalized Pauli operator, and from this we define the base point operator like this, and we define this discrete Wiegand function as a trace between the input state and the base point operator. Very simple. So how to use this for simulation? Now we focus on when the D is odd prime number. So look at this left figure. So we have the quantum state input, the low 1 tensor, low 2 tensor, low 3 tensor, and we assume D has non-negative Wigner distribution. I mean, this input state is positively represented. And the C1, C2, C3 is a Clifford operation, and M3, M1, M2 is Pauli measurement. The main fact is each Clifford operation, Pauli measurements and projection cannot induce, doesn't induce the negativity of the inputs. So I mean, if a low 1 tensor, low 2 tensor, low 3 get evolved under this operation, then the final state still has a non-negative Wigner distribution. From that, we can make a very simple classical simulation scheme. So we sample the base point from the distribution of the Wigner distribution of final evolved state, and just project it to a Z basis plot, given that we have a Z basis measurement at the last. And the interesting is we see the right figure. So this triangular shape is a Wigner simplex, the space of operators having non-negative Wigner distribution. And the circle is a space of the quantum states, and the hexagon shape is a space of stabilizer states. So you can see that there is intersection between these triangular and circle shapes and this intersection properly includes the state of stabilizer state. It means that not only for stabilizer states, but there are some mixed non-stabilizer states which can still be positively represented. So if we take these non-stabilizer mixed states as an input, we can still efficiently simulate this quantum circuit. And this circuit class properly includes the QD stabilizer formality. So we could naturally ask if we can apply to this discrete Wigner formalism also in the even dimensional system, like a cubic system, and these two. The answer is no. Let's say we have a quantum state, so pure quantum state, 2 copy of the F state. Interesting, this can be positively represented in the cubic system. So we have this non-negative Wigner function, and let's say we act the Hadamard or CNOT gates. So I denote that as a U-bell. This is a Clifford operation to make these 2 copy of state entangled. Then what happens for evolved state? It gets negativity. So this is a little bit awkward because actually most people know the Clifford operation is free operation. So we believe it doesn't induce any negativity, but really induces. So it means that when we measure the Pauli Jack basis or X basis to the input states at U low U dega, and now we cannot apply the sampling projection routine for simulation measurements as we do in the old point dimensional system. To cover this, we need to generalize Wigner formalism a little bit. So what we do is very simple. We just so here we have here actually we didn't have previously we didn't have this function. This FA vector is a binary valued function over the Z2n. We call this as a frame function. So we just add this frame function on the power of the -1. So that's all. So we redefine this base point operator like this. And now we define the Wigner function as a trace between input state and base point operator. So we call this as a frame Wigner function. So I show some examples. So the F state can be positively represented on the 0 frame. So when it's F is 0, I showed it before. But if we add the Hadamard gate, then it's not positively represented anymore, but still positively represented under a second Guedong frame, F equal A1x A1z. So the F state, which was here, goes to this way, and we have the Hadamard gate. So this doesn't belong to this 0 frame Wigner implant anymore. So we can see graphically. And the T state cannot be represented nor Z frame nor this 0 frame F equal A1x and A1z. But we can still express this as a convex summation of total 8 phase point operators of both 0 frame and 0 frame. And actually, every NQB quantum state can be convex on phase point operators of finite many frames. If it doesn't restrict the order of the frame. So the main strategy is we not only choose the base point. We not only so under the Clifford operation, we not only change the base points, but also we change the frame to find the Wigner function, Wigner structure under the Clifford operation. So let's say we have the input state rho, which was positively represented under the F. Then when we add the arbitrary Clifford operation U, then it gets negativity and fix the frame. But if we change the frame like this, if you set a new frame F prime, then with respect to this new F prime, then Wigner function doesn't lose the negativity. So this is just a intact previous Wigner function, but where the space point is symplectically transformed. So we have the tableau for symplectic operation and base function attaching for each Clifford basis, and from this we can transform any we can obtain any transform. So we can obtain any transform frame function under the arbitrary Clifford operation. Very fast. From this, we can make some new sufficient condition that we can classically simulate the adaptive Clifford circuits with positively represented input states. So let's say low is positive, low has positive representation with respect to f, and the final frame we could find the final frame f prime. So if f prime satisfies this condition, so when we substitute the zero vector to the x part, then it becomes linear. Then in that case we can classically simulate the final measurements. But unfortunately, this only holds for non-adaptive Clifford case, but actually, if we simulate the non-adaptive Clifford circuit with arbitrary positive input, then the polynomial hierarchy is collapsed. So this is still a very hard problem. So we think this is still meaningful. And the final frame has very complex structure. Actually, this condition doesn't hold frequently. Given that the initial frame is up to third order, then final frame is also up to third order. So actually, this form also usually is up to third order. So, but we could marginalize some qubits to make this final frame to be linear. So the left figure is the graphic representation of obtaining the due frame, and right figure is more important. So let's say we have the final frame and graph representation like this. So the shade ratio connecting three vertices indicates the third order monomial terms, and line connecting two edges indicates the second order monomials, and loop is for first order monomials. So since we have 7 vertices, this has 7 variable polynomial, third order polynomial. So let's say we marginalize a fourth measure, we marginalize fifth qubits, then we eliminate these fifth vertices along with all hyperedges having a fifth vertex as an element. So we have this graph. Now we marginalize first qubits, then we do the same thing. So we eliminate first and all connected harmonic edges. And now we marginalize 6 qubits, then only loop is left. So now the frame becomes the linear. In that case, we can simulate classical simulated circuits. So it means that even though we couldn't simulate the whole measurements, maybe we can still find some marginal measurements which can be classically simulated via frame unit functions. From this, we can measure the number of simulated qubits of the shallow random Clifford circuits. So the AB is for neighboring shallow depth Clifford circuits, and CD is for the complete graph Clifford circuit. I mean, complete graph structure is we at the each two Clifford block having no restriction on the locality. So from the AC, I compare the simulation results, 10 qubit simulation results of our frame unit simulator with the Christie AR simulator. So it perfectly matches each other. It means that our simulator works very well. And from BND, we can see that by increasing the number of qubits, the number of simulated qubits in average increases quasi-linearly. And from D is the complete graph structure. So we can see that there is some pronounced shift of the upward trend by increasing the scale factor of the depths, circuit depths. So we think that there might be some transition threshold of this scale factor. So we did some finite size scaling of this D graph, and conjecture that this threshold scale factor might be a 0.81, which is actually very near to anti-concentration threshold. Anti-concentration means at which the measurement probability gets very flat. So indeed, no concentration. So we think there might be some deep connection between them, but I believe this is a problem. And also, we compare the simulation speed with Quiz-Key simulator and propose neighboring and conflict default circuits. We observed very significant speed improvements over the AI simulators. Yes, because the number of measurable qubits increase linearly. So actually, via the brute matrix calculation scheme, the total time complexity is 2 to the proportion, the constant proportion of the n, so still exponentially large. That's why the pure AI simulator takes very less time. So these are our results. So take message is we have introduced the framing of function combination of branching rules that induce negativity under the NEP4 gates. And second, we establish sufficient condition for efficient simulation of non-adaptive Clifford circuits via framing of mechanism. And third, we construct systematic protocol to find marginal outcome measurements that can be efficiently classically simulated by solving vertex store problem. I mean, eliminating vertex and connecting hybrid edges. And from this, we measure the average number of simulated qubits for both the 1D and conflict graph architecture shallow Clifford circuits. And the future problem might be to inspect several adaptive Clifford circuit. In which we can still make some efficient classical simulation looking here. And also, actually, the all pure state we have experimented is a single qubit pure state. But actually, there is a non-stabilizer entangled state which have positive representation under the non-local frame like F equal A1x A2x. But we didn't find the entangled positive representative pure state. So maybe we should prove the existence or non-existence of positive representative pure states under such local frames. So this will be our future problem. So if you're interested, please check this archive file. And thank you for your attention. Thank you very much.
We are a little short on time, but we have time for 1 or 2 questions. Anyone else on the audience? Okay, great. Andrew there at the back.
I'm just wondering if you have looked into this frame discrete Wigner function on a non-universal computational model such as IQP.
Yeah. In this. So let me ask you a question also.
Yeah, I'm just wondering if you've looked into if it's the possibility or impossibility of having efficient simulation using your frame Wigner discrete Wigner function on some non-universal computational models such as the IQP circuits or
Okay, very good question. So we haven't explored yet because we actually usually focused on the Clifford operation and the base point and branching rule of the Clifford operation. Actually, in general, the IQP circuit contains no Clifford gates. In that case, as we said, the default state can still be possibly represented via the multiple frames, but we didn't find the efficient way to track this base point and inflating multiple frames. So, yeah, very good point. So, also we should explore this, but not yet. Yeah.
Thanks. And I think we had one last question in the back somewhere. Oh, good. Okay, great. In that case, we will now have our afternoon tea, and let's get back here around about 3:50 for